All right, so we are apparently recording, so we will work through this. Okay, so we're going to solve exponential equations today. And this one can be a little bit tricky, but it's not terribly bad. So what we're going to do is we're going to use properties of exponents to simplify each side. We're going to rewrite the equation so both sides have the same base. Then we're going to drop those bases and set the exponents equal to each other and solve those. So in number one, now you're going to always come up with an answer. There are no undefined or no solutions when it comes to exponents. Exponents can be anything. So if you notice in problem one, both of the base numbers are a 2. Do y'all agree? That's ideal situation. So I'm going to take the first exponent, which is x plus 1. I'm going to set it equal to the second exponent, which is 9. And then I'm going to solve that equation. So x equals to 8. You can quickly check it if you plug that back in right here. There we go. If you plug that back in right here, 8 plus 1 is 9. So you get 2 to the 9th equals to 2 to the 9th. So it works out. Okay. Same thing here. I have bases of 5. So once you have the same base, you drop the base, you set the exponents equal. So 4n plus 5 equals to n minus 7. And you solve that. So I'm going to move that n over, so that gives me 3n plus 5 equals to negative 7. I move the 5 over, that gives me negative 12, and when I divide, I get n equals negative 4. Everybody okay with that one? All right, now I have all 3 bases of n, but what do I do with the exponents? So let's go back and talk about our properties of exponents. If you have x to the n times x to the m, that gives you x to the n plus m power. When you multiply like bases, you add the exponents. You do not multiply the exponents, you add them together. Okay? If you had a division problem, that's where you subtract the exponents. You take the bottom exponent up and you subtract it from the top exponent. Those are your properties of exponents. We're going to do the same thing here. I have all 3 bases, but since I'm multiplying these two, I'm going to apply this property. So I'm going to take k and add it to k plus 2. Then I'm going to set that equal to 5k minus 1. A lot of people want to multiply those exponents together, but you're technically adding them together. That's the exponent rule. So that gives me 2k plus 2. You are not distributing that k, you're simply adding like terms, equals to 5k minus 1. Now, it's totally up to you which side you want to put k on. Do you want to move the 2k to the back or the 5k to the front? So you want to move the 2k to the back. So we're going to subtract 2k from both sides. Good call. So that would give me 2 equals to 3k minus 1, which means I'm going to add the 1 to both sides. And I get 3 equals to 3k. So k ends up equaling to 1. Now, in example 4, they're using this property again. It's just an additional example to remind you that when you have like bases and you multiply them together, you add the exponents. So negative 4 plus 9 on the left Since I have like bases on the right, I'm going to take v plus 4 and I'm going to add that to the second exponent. So I get 5 here. V plus 2v is 3v. 4 plus negative 11 is negative 7. I'm adding like terms over here, so combine like terms. V plus 2v is 3v. 4 plus negative 11 is negative 7. I'm going to add 7 to both sides. That gives me 12 equals to 3v. Divide both sides by 3, and v will equal to 4. Any questions about the first 4 or using the exponent property to add those exponents? Now, in the next set, type 2 equations, these are equations without common bases, but you should be able to change them to common bases. Okay, so on the left, I see a base of 6. On the right, I see a 36. I can rewrite 36 as a base 6 number. Do y'all agree that 36 is the same thing as 6 squared? 6 times 6. So I'm going to rewrite the right-hand side to have a base 6. Now that I have my bases the same, we can do what we did in the first 4. Drop the base, set the exponents equal, and solve it. So add 10 to both sides. That gives you 12. Divide by 2, and you get 6. In example 6, we have a base of 2. My guess is that we can turn 8 into a base of 2. Now, it's not 2 squared because 2 squared is 4, but what is 2 to the third power? It's 8. So I'm going to replace 8 with a base 2 to the third power because 2 to the third power is 8. Now, I just started playing around with base 2 because the left side had a base 2 and 8's not a base 2. Once I get those bases to be the same, p minus 7 equals to 3. When you add p, you end up with p equals to 10. Now, I know I'm kind of going out of order, but I'm going to do number 8 before we do number 7, simply because number 8 also has a base 2. So now that base 2 kind of indicates to me that 32 is probably a base 2 number. So we already did 2 squared. We did 2 to the third. 2 to the fourth would be 16. And 2 to the fifth would end up being 32. So I can change 32 to a base 2 number. So 32 changes to 2 to the fifth. The right side does not change. And then from there, you set your exponents equal. 5 equals to 2m minus 9. Add the 9. We get 14 equals to 2m. So m equals to 7 when you divide both sides by 2. Everybody okay so far? Now put a star by number 7 because it is a little bit different. I do see some 7s. Do y'all see 7s? The only problem is this 7 is in the bottom of the fraction. If I could just move that 7 to the top of the fraction, it would be good. Now here is the negative exponent rule. Negative exponents. If you have x to the negative n power, that's the same as 1 over x to the positive n power. That property also goes the opposite direction. If you have 1 over x to the n, you can rewrite that as x to the negative n power. So that property goes backwards. So what I'm going to do with that right-hand side, since that 7 is in the bottom and I need it in the top of that fraction, I'm going to write it as 7 to the negative 1 power, because the understood exponent that's already there is a 1. By doing that, I've got like bases. You drop those bases, set your 4x plus 11 equals to negative 1, and solve the equation from there. So 4x equals to negative 12, and x would equal to negative 3. So that's a tricky one, simply because you have to move that number out of the denominator up to the numerator. So I would just make it a negative exponent. All right. For number 9, the smallest base I see is a 3. So I'm going to start with that and see if I can change 27 to a base 3 number as well. So 3 squared is 9. 3 to the third is 27. So I can replace 27 with 3 to the third. But notice there's already an exponent out there. So we've got 3 to the third times 2x plus 6 equals 3 to the 2x power. Now I'm multiplying these together because it's not a 3 times a 3 in that bottom like it was when we were up here with the tens. Okay, it's just 1 3. So I'm going to distribute this and set it equal to 2x. So 3 times 2 is 6x. 3 times 6 is 18. And that gets set equal to the 2x that's on the other side. So I distributed here. That's where I got the 6x plus 18. So this time, I'm going to subtract the 6x. That gives me 18 equals to negative 4x. You always divide by the coefficient of the variable, so we're going to divide both sides by negative 4. And that would reduce to negative 9 over 2 for your x value. Not all of these are going to end up to be nice, neat, evenly divisible numbers, okay? And it's okay to come up with fractional answers for your exponents. Would anybody like to guess at what the base could be on number 10? 4 squared. I have a 4 here, so I can change that if I take 4 squared. Very first one, 16. So I'm going to change that to a 4 squared. So 4 to the y plus 2 power equals 4 squared. Multiply that by the exponent that's already there. So we're going to distribute that exponent over here. So on the left, we have y plus 2, dropping those bases. That would be 2y minus 6. And then we go from there. So I'm going to move the y to the other side. So that would be 2 equals to 1y minus 6. I'm going to add 6 to both sides, so y ends up equaling to 8. Any questions about those? Now, the third set of examples that they're going to give you, or that I'm going to give you, is what happens if you have to change both bases, okay? A lot of times you can see or get kind of a feel. Now, 25 or 125 and 25, I can change both of those to base 5s. If I do 5 squared, that gives me 25, but what do I get when I do 5 to the third? I get 125, okay? So this time I'm going to have to change both of the bases, but at least I can change both of them to a base 5, even though that exponent's different, and that's okay. I can get them to a base 5. So this would be 5 to the third, and we're going to multiply that by y, the exponent that was already there, and we're going to set that equal to 5 squared. So drop the base, keep the exponents. 3 times y is just 3y. Divide both sides by 3. You always divide by the number attached to the variable, and that would be your final answer. Now, number 12, 8 squared is not 16. And a lot of people like to say that 16 is the same as 8 squared. It's not, okay? Now, even 4 squared, that gives me 16. But what 4 to what power would give you 8? Okay, so I have to go smaller than that. Both of these are 2's. 2 squared is 4. 2 to the third is 8. And 2 to the fourth will give you 16. So I had to go all the way back to a base 2 number to get these to the same base. So 2 to the fourth replaces 16. Multiply by that 3x. Then I have 2 to the third, which replaces the 8. And you're going to multiply there. So on the left, I get 2 to the 12x power. 3 times 4 is 12. Here, I actually physically have to distribute. So 3x plus 6. Now that my bases are the same, we do what we've done in every example. Drop the base, set the exponents equal. So I end up with 9x equaling to 6, and x equals to 6 divided by 9, which is 2/3, when you reduce it down to 2/3. Now, based on what we did here, I'm going to pause for a moment and let you come up with the basis for number 13. All the information that you need is in the circle. right? That's what I got. I took 4 out and replaced it with 2 squared. I took 8 out and replaced it with 2 to the third. Multiplied those exponents and got 6x. Distributed here, got the 3x minus 3, and then solved from there. How'd we do? Okay. Now, star by number 14 because it's got that negative exponent rule. And the only reason I know it has the negative exponent rule is because I have a fraction. Okay. So the first thing I'm going to do is I'm going to do 3 to the negative 1 times the 2x. I have to get that 3 to the top, and the only way to do it is to use the negative exponent rule. Now, since this base is a 3, this base should probably be a 3. So 3 squared is 9. 3 to the third is 27. But 3 to the fourth is 81. So I'm going to change that to 3 to the fourth and multiply it by the 2x plus 5, the exponent that's already there. So when I distribute here, drop in my bases, I get 8x plus 20 equals to negative 2x. I'm going to subtract my 8x from both sides. So that gives me 20 equals to negative 10x. So negative 2 will equal to my x value. Now, I hear the lunch cart, so we got one more. Do you want to see 15 or do you want to see 16? 15. All right. So if I think about 8, 8 is 2 times 4, correct? If I think about 32, I've got some numbers in there, but unfortunately, 8 is not 4 squared. Okay? Even if I do 4 to the third, that's 64. So base 4 is out. So I'm going to break it down to a base 2. 2 to the third will give me 8. We've done that several times. You've already got that several times on your paper. 32 is 2 to the fifth. So I can break both of those down to 2s, base 2s. So 8's coming out and 2 to the third is going in its place. 32 is coming out and 2 to the fifth is going in its place. I'm going to distribute that 3, drop my base 2's, so that gives me 6a minus 3 when you distribute 3. On the right, I'm going to distribute 5. So that is going to be 10a plus 5. And then I have to solve that from there. So I'm going to subtract 6 from both sides because I like positive a's. Then I will subtract 5 from both sides. That gives me negative 8 equals to 4a. So our final answer would be negative 2. All right. Any questions about exponential equations converting to like bases? Because after lunch, we're going to get into some logarithms. All right. Perfect timing. All right, so hopefully it's recording this screen and not the other one like it did the last time. We will have to see. All right, so we're going to talk about logarithms in this one, which is the reverse of the exponential. So I hope you have a calculator. And on that calculator, I want you to look for a LOG button, and then an LN button should be pretty close to it. Okay. Now, the first few examples, we're just rewriting. We are not pressing buttons on our calculator. Okay. Because when you have a logarithm, the first thing you need to understand about logarithms is they are actually exponents. When you push the button on your calculator, you're creating an exponent. So every time you hit that logarithm button, an exponent comes out. So what we're going to do is we're going to take this logarithm and we're going to write it in its equivalent exponential form. So the way you do this is you always start with the base number. That base number is going to equal to the number on the other side, or not equal to, but it has the exponent, and then that's going to equal to that a value next to it. So I always draw a circle, but I start with my base number first. Okay, so start with your base, set it the power, so b to the x is equal to a. So when I rewrite this expression in exponential form, which you're going to be asked to do on Math Excel, you start with the base number, which is 3, raise it to the second power, and set it equal to 9. And that makes sense. 3 squared does equal to 9, so that's a legitimate value. What would you do with number 2? 6 to the third equals to 216. It's the same pattern over and over and over again. All right. Number 3, 7 to the 0 power equals to 1. What about number 4? 2 to the 4th equals 16. What about number 5? Start with your base. To the what power? Equals to, perfect, 1 over 16. And then the last one, start with your base. So that would be 9 to the 3 halves power equals to 27. Now you can check every single one of these in your calculator. 7 to the 0 will provide a 1. 2 to the 4th provides 16. 9 to the 3 halves power will give you 27. So you can check all of those on your calculator. Now, we're going to go backwards. We're going to write each one of these equations in its logarithmic form. We're not solving it, we're just rewriting it, okay? So, always start with the base. So we're going to start with 14. Log, and then you're going to drop that 14 down just a little bit like all these other bases were up at the top. Go full circle. Log of this number, 196, equals to 2. So log base 14, 196 equals to the exponent. The exponent is always over there where the equal sign goes. Start with your base. Log base 3. Go to the other side of 81 equals to the exponent 4. Kevin. I don't have her marked absent. Yeah. Bye. All right. So what about number 9? Log base 12 of equals 1. All right. What about number 10? Do we need to do the last two, or do you kind of think you have the rewrites? I can do the last two if I need to. Anybody need to see them? Okay. So rewriting, when we go to start solving equations, that's going to be important. Now on the next page, what we're going to do is we're actually going to press the buttons on our calculator. Okay. A logarithm with base 10 is called a common logarithm. This button on your calculator, you will not see it. Your calculator doesn't say it. But this log button has an understood base 10 attached to it. So every time you hit it, you're telling me log base 10 of something. Well, if you notice, this is a base 7, this is a base 3, so on and so forth. Okay, so all these bases are different. So what we're going to do is we're going to do what they call change of base, and we're going to use our calculator. So what we'll do is we'll take log of x and divide it by log of the base. Now the base number is not always a 10. Okay. So in order to calculate the exponent, because we're about to hit the log button, we're going to take this problem and we're going to do log of 49 divided by log of 7. That now changes it to a base 10 number, and I can press the button on my calculator. If you are having issues, I get the answer of 2. If you do not get 2, please make sure you do not leave this room without me helping you with your calculator. So what that means to me is that the base 7 raised to the second power will equal to 49, and it does. You are finding the exponent on this base that produces the number 49. So here, I have log 27 divided by log of 3. What do you get when you divide log 27 by 3? Log 3. 3. Did I do something wrong? Did I do something wrong? Okay. All right. Now, do you see a visible base? A visible base is a visible base, like the 7 and the 3. When there is no visible base on an LOG log, there is an understood 10 right there, which means all you have to do is just type in log of 100. It's automatically a base 10, and if that is a base 10, all you do is you press that button. So you just hit log of 100, and you get 2. So on 16, we're going to do log of 1 divided by log of that base number. Did you get 0? All right, what'd you get for 17? Okay. Now, This fraction number, if you get a negative, that's why. If you notice none of our other numbers, none of these numbers, not the base number, but the number, were fractions. But now that we have a number that's a fraction, you're probably going to get a negative answer. Did you get negative 2? Mm-hmm. Now, the other thing to watch out for is when your base number is bigger than the number itself. That should give you a fractional answer, maybe even a decimal answer. So if you take log 4 and divide it by log of the base 64, what did you get? 1/3, or you might have gotten 0.3 repeating. Okay, everybody good there? All right, so your class assignment today is going to be extremely easy. I want you to take these 6 problems and we're going to do the same exact thing, change of base. You are to take, if you did your half sheet of paper the other day, take the other half out and you can do these on a half sheet of paper. You do not have to submit a full sheet of paper. We're doing exactly what we just did. This is change of base formula. So you're doing exactly what you just did. All right.